All right, here we are. Yep, looks like most of us are here. All right, so we got a couple of things to do today. For one thing, we have a problem set to work on. This is problem set number 1 from chapter 5. There's 3 of them all together. And so what I'd like to do is go over the first one today, and then we'll do the second one on Thursday, and I guess we'll save the third one for next Monday. And then with whatever's time is left over, we'll get back to 5C, where we were starting to look at scientific notation. Okay, so now these problems are meant to be very similar to what's actually on the first midterm, which is coming up not for a while, down the road a bit. Most likely it'll already be early March by the time we actually get to it. But, we still have to finish chapter 5. We have to get through 6, and we've got more practice problems to work on. So I'd give it a good 3 weeks at least before the first midterm. So anyway, why don't we carry on with this one? So we start with 16. All right, now we know that every number has at least the factors 1 in itself. So we'll start with 1 and 16. So you don't have to do it this way, but I think it's easier to start writing out a list of all the factors. Start with 1, and of course you'll have 1 with 16, 2 in this case with 8. It's not divisible by 3, and then it's divisible by 4. Now, you don't have to go any further because the next factor would be 8, which we already have up here. So you can just write out the list: 1, 2, 4, 8, and 16, and that's it. There are no more. You don't have to repeat any of them, so you're done. Excellent. All right, that's all I had to do for that one. Now remember, these are not the prime factors, by the way. These are just all the factors, prime or not. So if it wants prime factors, it'll specifically say that. All right, now how about 225? Now this one probably has quite a few. For obviously 1 and 225, not 2. How about 3? How can we tell if it's divisible by 3? Well, here's a fun little side note. If the sum of the digits of a number is a multiple of 3, you may have heard this rule before, then the number is divisible by 3. So in this case, let's add this. You can see that here, the sum of the digits is 2 plus 2 plus 2, 5 rather, equals 9, which is divisible by 3, or let's say this is a multiple of 3. Therefore, 225 must be divisible by 3. All right, so that means, in other words, it helps if we know in advance that it is definitely divisible by 3. That way, all we have to do is look for that other factor. So it turns out here that it's 3 times 75. All right, so that rule you may have heard before. The sum of the digits is a multiple of 3. Therefore, it is divisible by 3. Now, some of the other ones are more obvious, like 5. You can tell a number is divisible by 5 if it ends with a 5 or a 0. Now, it turns out there actually are rules for all the digits, but some of them are so complicated that it may not be worth your while to memorize them. But the 3 one, I think it's really simple. You might as well, at least recognize this when you see it, because it could come in very handy. Some of the other ones, well, that's a different matter. Like there's a rule for 6, which is very complicated. There's one for 7 and all this and that. But in those cases, you might be better off just taking out your calculator and dividing it and seeing if it is in fact divisible by that number. Anyway, 4, no. Now you can see why, because this is clearly not an even number. How about 5, though? I did say just a minute ago that any number that ends in a 5 or 0 is divisible by 5, and I'll make a note of that here. Any number that ends with 5 or 0 is divisible by 5, so you don't have to worry about that one. And it turns out that this is 5 times 45. Okay, are there any more? How about 6? No, it doesn't look like it. 7, I don't think so. 8, it's not even. How about 9? How about, well, that would be interesting. If we divide this number by 9, just to make sure, let's take out the calculators. Oh my God, it turns out to be 9 times 25. That's right, exactly. How about 10? No, that's a different case because any number that ends in 0 is divisible by 10. I mean, I think that's pretty straightforward. I'll just remind you here. So this one is not divisible by 10. Then we have to try some of the higher ones, 10, 11, 12, no, 13, I don't think so. Oh, wait a minute, how about 15? It turns out that 225 is 15 squared. So once we get to this point, you don't have to go any further because any higher numbers like 16, 17, 18, etc., would be reflected up here already. So once you hit this point, you can just stop because you've got them all. 1, 3, 5, 9, 15, 25, 45, 75, and 225. And that's it, you're done. Okay. Well, what else do we have here? 126. Now, 126 is even, so it's likely to have a large number of factors. For example, 1 times 126 itself, 2 times 63. Look at that, 3. Now, how can you tell it's divisible by 3? Because the digits add up to 9. And in fact, it's 3 times 42. How about 4? Oh, not 4, not 5, obviously. How about 6? Yeah, look at that, 6 times 21. 7, no, 8. No, it doesn't look, oh, wait a minute. Is it possible that this one is divisible by 9? Let's see, 126 divided by 9? 14, how do you like that? 10, no, 11, no, 12. Oh, wait a minute, I think I missed one. You know what? I did. Surprisingly enough, I just realized I went past one of them. This one actually is divisible by 7. Yeah, see, sometimes they surprise you, these numbers. But not 8. We do have 9, not 10. I think that might be it. Yep, we got them all. Okay. All right, great. So you can write it as a list. 1, 2, 3, 6, 7, 9, 14, 18, 21, 42, 63, 126. All right, and then finally we have 54. All right, 1 times 54, 2 times 27. This one's divisible by 3 because the sum of the digits is 9. And that's 3 times 18. 4, no. How about 5? No, that doesn't look good either. 6. Wait a minute. 6 times 9. All right, 7, no. 8, I don't think so. No, it looks like we're done. Okay, 1, 2, 3, 6, 9, 18, 27, and 54. All right, so basically this is sort of a brute force approach. In other words, you're just grinding through all the numbers until you find them all. I don't think there is a more sophisticated approach that we could use here. Like with prime numbers, how do you, I'm sure there's a computer program that'll help us identify prime numbers, but to do it yourself, I believe all you can really do is just write them out and just identify the ones that are prime. Now, multiples are easy. Okay, what are you doing with multiples? You're just literally multiplying them by the first 5 natural numbers in this case. So you've got 3, 6, 9, 12, 15, done. All right, see what I mean? You just literally multiply your number by 1, 2, 3, 4, and 5. So here we have 7, 14, 21, 28, and 35. Then for 10, well, 10 couldn't be any easier. 10, 20, 30, 40, and 50. 12, we have 12, 24, 36, 48, and 60. And then finally we have 15, 30, 45, 60, and 75. All right, let me just leave it there for a minute so you can get caught up. I think I got a little too carried away there. So let's leave them there for a second. So you can catch up. And then the next batch is prime factors, I believe. Yeah. No, there's one more down there somewhere. All right. All right. So scroll down just a little more. There's also the multiples of 5. So you can see some of these are quite simple. Some of these, yeah, you want to be a little careful. I mean, you might be able to do these in your head, but you always want to be careful. Okay, so then the next batch of questions, we're looking for the prime factors, which is a little different. And so for these, you might want to find yourself drawing the binary tree to help yourself identify all of the prime factors. All right, for example, let's try. The first one is 16. Let's see how that works. Here we go, 16. So let's do the tree. So we start with 16. Now, the order in which you do this doesn't make any difference, as we've seen. I'll try 2 times 8, but I could have just as easily done 4 times 4. I'll end up with the same result. And when you're done, no matter how you follow this tree, you're going to wind up with 4 2s. And you could abbreviate this to the 4th if you want to, because of course it means the same thing. All right. So the key here is that the product of those numbers gives us 16, and there's no other way of expressing this as a product of primes. It's unique to that number. That's what the fundamental theorem of arithmetic tells us. Now, 18 might be a little trickier. Okay, so because it's an odd number for starters. We can do 3. Oh, no, this should be easy. We have 3 times 6. And the 6 can be broken down into 2 times 3. That should be it. So we wind up with 2 times 3 times 3. That's it. So yeah, a small number like 18 shouldn't have too many prime factors, but then the next one, ooh, it's going to have a lot. All right, so let's try the next one. But at least now we remember how this works. I mean, the idea here is that no matter how big the number is, you just continue until we're done. It's not more difficult with the bigger number. It's just that it's more time consuming. And when you see an even number like this, probably your best bet is to start with 2 and whatever divides evenly into that. Like here we have 648. And that's even as well. So let's do 2 and 324. And this one is even as well. So let's try 2 and 162. Even again. Here we go. Our first odd number. Now you know that 81 is 9 squared. So why don't we try 9 times 9? Or you could have done 3 times 27. And then each of these is 3 and 3. All right, that's a lot of factors. Look at that. So 1296 equals, so we've got 1, 2, 3, 4 2s and 4 3s. And that could be written, as you know, as 2 to the 4th times 3 to the 4th. It's the same thing. And so this is your final result. All right, what's next? 1960. Now you might think 1960 has an enormous quantity of prime factors, but not necessarily. Let's try it. So we'll start, it's even, we may as well start with 2. 1960 divided by 2 is 980. That's right. Then we have 2 times 490. 2 times 245. See, now this one is divisible by 3. No, it's not. This is a 5. If you divide 5 into this, you get 49. And then the 49, of course, is 7 squared. And both 7 is prime. So this one turned out to be a little quicker than we thought. We got 3 2s, a 5, and a pair of 7s. Okay, and if you want to, you can write that as 2 cubed times 5 times 7 squared. All right, and if you're not sure that you've done it correctly, multiply them out. 2 times 2 times 2 times 5 times 7 times 7, it is indeed 1960. Beautiful. All right, now what about 17? Now 17 is at the other extreme of complexity because it is a prime number. So the thing is about this case is that when you have a prime number, 17, now remember, we do know that 1 is not prime. Therefore, in this unusual case, 17 is the only prime factor of 17. So this is one of the unusual things about prime numbers. They only have one prime factor. They have 2 factors, but only one prime factor. Compared to all the composite numbers, which always have at least 3 factors, of which at least 2 are, well, it could be any number of primes, but they always have at least 3 factors. So this is that bizarro case that you have to be aware of. Okay. Now, how about these greatest common factors? Now, these also require the use of the trees, because remember how this works with greatest common factor. What we're looking for is the prime factors that they have in common. So I'll make a note of that right here. We're going to try to find the prime factors that 3 and 9 have in common. This is how you do it. So basically what you can do is draw 2 trees. Ooh. 3 is prime. The only prime factor of 3 is 3. Whereas with 9, we have 2 prime factors. They're both 3s. So 3 and 9 have only one prime factor in common. And that would be the 3. 3 and 3. So for this particular pair, the greatest common factor is 3 because that's the only one they have in common. There is no larger prime value. There is no other value that evenly divides into both of them. Now, most of the time, it won't be like this. But yes, if they're both prime, or one of them is prime, you will run into this situation. So just remember, 1 is not considered to be prime. Now, how about 10 and 35? This is different. Neither one of them is prime. There should be a greatest common factor between them. Let me just move this down here to make some space. So we're going to have two trees. This one is easy. How about this one? Man, it couldn't have gotten much simpler. So the prime factors here are 2 and 5. Actually, the way it's not 2 comma 5, 2 times 5. All right, you know what? Let me write it like this. The prime factors are 2 and 5, but what we want to do is write it as 10 equals 2 times 5. That's better. Over here, we'll say that the prime factors are 5 and 7, but this is what we're really interested in. 35 equals 5 times 7, and the one factor they do have in common is here, 5, and that implies that 5 is the greatest common factor, which you can feel free to abbreviate GCF if you want to, of 10 and 35. Also, remember, when you're in high school, you may have been, this also is referred to as the greatest common denominator. You do hear that as well, but it means the same thing. All right. Now, here's an interesting case. What do we do with this one? So 1 is not prime, so the only prime factor of 7 is 7. What about 10? Oh no, the prime factors are 2 and 5. Well, what happened? They don't have any in common. What do we do now? All right, this is an interesting result. All right, so in this case, 7 and 10 do not have any common prime factors. Therefore, we say that their greatest common factor is 1. All right, so formally, we're going to say that when they have no prime factors in common, they still have a factor of 1. Okay, 1 is still a factor, even if it's not prime. So we're going to say that their greatest common factor is 1. And in addition to that, when this happens, we say that 7 and 10 are relatively prime, which is kind of an interesting idea. In other words, they're not necessarily prime numbers, but compared to each other, they are. It's not possible to find a common factor between them other than 1. So this is an exception. Remember, we'd said before, the greatest common factor is the prime factor, are the prime factors they have in common. When there aren't any, we just say that their greatest common factor is 1, because obviously 1 divides evenly into both of them. So that's a tricky case. Okay, so the answer is not no common factor. The answer is there is one, but it's considered to be 1. All right, now what about this one? 6 and 11. Uh-oh, I think we're in for trouble here too, because look what happens. The prime factors are 2 and 3. And 11, oh no, the only prime factor here is 11. So guess what? It's the exact same scenario. Since 6 and 11 have no prime factors in common, their greatest common denominator, their greatest common factor is defined to be 1. End of story. And again, they are relatively prime. And again, it's not the case that they're both prime, but relative to each other, they're considered to be prime. Wow, what a strange idea. Relatively prime. Okay. Now, common multiples. What do we do with these? Now, remember what multiples are. We just literally run through the list of the natural numbers and multiply them by our number. But here we're looking for the one they have in common. So let's do this. Let's write out the multiples of 5. And we can, it's hard to say when to stop in a case like this. Just write out a few. And what we're looking for is the first time they have one in common. Oh, we can stop. Why? We've already got our answer. Oh, I almost forgot the dots up here. Okay, so in other words, you can see what I mean. So the least common multiple, we say, of 5 and 10 is 10. I'll make a note here. Sometimes the least common multiple of two numbers is one of the two numbers. It does happen, and it happened here. It's just one of the two. 10 is itself the least common multiple of both of them. Not that it happens a lot, but it does happen sometimes. And I just thought I'd throw that in there. All right, what about this one? 12 and 24. 12, 24, 36, 48, 60, 72, ... Multiples of 24. 24, oh, here we go. I could stop right now because I can see that the answer is 24. And again, the same thing happened. It was one of the two numbers. Okay, so the least common multiple of 12 and 24 is 24. Okay, let's try 5 and 7. So there's 5. 7, 14, 21, 28, 35. Oh, here we go. I found it. That one took a while. Okay, so the least common multiple of 7 and 5 . 35. And a note in parentheses here, sometimes the least common multiple is the product of the two numbers. And that's what happened here. It does happen. Okay. It's not that unusual. I mean, it happens. It depends on the numbers. Now, finally, we have one more. The least common multiple of 6 and 10 was 6, 12, 18, 24, 30, 36, 42, ... For 10, 10, 20, 30. Oh, here we go. We can stop. How do you know? Because we found our answer, 30. Okay, so the least common multiple of 6 and 10 is 30. End of story. All right, this time it wasn't either one of the numbers, it wasn't their product. It can be anything. So here it was 30. Okay, now we got some word problems. Now I know that people usually are concerned about word problems, but the trick to word problems is just making sure you understand what kind of problem it is, and the rest is just the techniques that you're used to using. Yes, I know, word problems. I know from experience, people will be, if I could hear what you were doing, you'd be moaning and groaning right now at the thought of word problems, but you wait and see. They won't be that bad, at least not this time. Yes, if we had a survey, in fact, I don't know if it's worth my while to do a poll, but if I took a poll and said, who likes word problems, I'm going to guess that nobody would say yes. It's just, it's pretty scary stuff, but it doesn't have to be. So like, here's an example. Let's take a look at this one. We have two people who are bicycling on a circular trail. Okay, they're going around a big circle. And let's just say they go clockwise. Okay, well, that's not the best one. They're going this way. This is the starting point right here. Now, the first person can get around that trail in 24 minutes. The second can get there in 36 minutes. Let's say they start together, but they don't ride together. They just start together. When they're riding, one person is going 24, will only take 24 minutes. The other will take 36. So clearly one of them is much faster than the other one. When will they be at the starting point at the same time? Again, in other words, when will they catch up with each other? Let's say they've agreed that they will continue to bicycle until they both find themselves back at the starting point at the same time. Then they'll go to lunch. All right. So they're both eagerly looking forward to lunch. But first we have to get around the trail, and we have to wait till both of them gets to the same point. And there's no cheating. They can't slow down or speed up. They're going to maintain a consistent speed. Now, here's the trick. You have to visualize how often is each person going to come back to the beginning. So person one, we'll call them person one. No, this will be Phil. Okay. And so Phil rides really fast. Phil will reach the starting point at the following times. All right. After 24 minutes, and again after 48 minutes, and again after 72 minutes, if he isn't too worn out, 96, 120. And then let's say that the other bicyclist is, I don't know, Sharon. Sharon will reach the starting point at the following times: 36, 72, 108, 144. Oh, look what I've just discovered, almost by accident. It turns out that in 72 minutes, they'll both be back at the starting point. So exactly what have I just done? This shows that the least common multiple of 24 and 36 is 72. Therefore, Phil and Sharon will be back at the starting point in 72 minutes. Well, they'll be good and hungry by then, let me tell you. But yes, so it turns out this was just a least common multiple problem. Now, when you're asked about a least common multiple problem like this, it's easy. But here it's been disguised as a word problem. So once you realize that this is nothing but a least common multiple problem, it's just as straightforward as it can be. So this is where the practice comes in, getting used to these types of problems. You can see right away, well, after a while, that this is nothing but a least common multiple problem. Okay, so yeah, I can see it's a little challenging. It might take a while for you to recognize that this is a least common multiple problem, but once you do, of course, it's easy. Yes. Okay, so you notice how I didn't fill it up with a lot of unnecessary details. Sometimes some books love to do that. Like I could have said, it's raining and, they're expecting snow next week and, well, all this irrelevant stuff. No, all that we care about is that it takes 24 minutes for the first person to ride around the track and 36 for the second. And sooner or later, they'll catch up with each other. When will that happen? That's 72 minutes. Well, that being the case, let's take a look at this one. We've got lighthouses. Now, the purpose of a lighthouse is to flash and make sure ships don't crash on the shore late at night when it's too dark to see anything. So they're going to be flashing, but they're going to flash at different intervals. And this is how we can tell which one is which, by the way. So the first lighthouse flashes every 10 seconds. The second one every 15 seconds. The third one is every 20 seconds. And the fourth one is every 30 seconds. And if all four of them start at the same time, let's say they're all turned on at 8 o'clock in the morning, and they're flashing, 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 how often would we see all four of them at the same time? Well, guess what? This is another least common multiple problem, but it's applied to 4 rather than 2 lighthouses. And that's certainly fine. Lighthouse 1, every 10 seconds. So it'll flash in 10, 20, 30, 40, 50, 60, 70, 80, etc. seconds. Lighthouse 2 will flash it's 15 seconds, 15, 30, 45, 60, 75, 90, 105. That's probably good enough. Lighthouse 3 is going off every 20 seconds. So that's going to happen in 20 seconds, 40, 60, 80, 100, 120. And then finally, we have lighthouse number 4, which goes off every 30 seconds. All right, so if we look at all 4 of these, I think we can find what they have in common. Let's see. Oh, look at this. In 60 seconds, they'll all be flashing at the same time. And then, of course, they'll be off from each other. And most likely the next time will be 120 seconds because the pattern never changes. Okay, so here, the lighthouses will all flash again, or flash at the same time in 60 seconds. And this is the least common multiple of 10, 15, 20, and 30. So more formally, that's what we're really being asked to do. And so you can see the least common multiple can actually be applied to 2 or more numbers. And the same thing holds true for greatest common factor. It's not just restricted to 2. We could ask for the greatest common factor of any number of values that we choose. All right. Now, I will be posting these solutions on Moodle later on today, I guess. And you can go through them. And if you have any questions about this one, we can go over them on Thursday. And then what I'd like you to do is do number 2 for Thursday. 2 is a little bit more involved, as you can imagine. But it's excellent practice. And just keep in mind, the actual exam will be very much like these questions. Very much. Okay, the idea is that I'm not trying to trick you. I'm not trying to unnecessarily complicate them. I just want to make sure you understand the material. So if you understand what we did here, you'll be in excellent shape when you get to the test. Okay. Oh, good. Yes, because I know you probably had classes where you were tricked. That won't happen here, believe me. Everything is meant to be as straightforward as can be. It's like, here's the material. If you get it, you get it, and you're fine. No trickery here. In fact, the trick is that you're not being tricked. That's the way to look at it, I guess. It's very Zen. No trickery here. All right. So anyway, that means it's time to go back to what we were doing the other day, which is scientific notation, which is not hard. It just takes a little getting used to if you've been away from it for a while. So like I was saying the other day, you probably saw it in high school chemistry or physics, possibly biology, although biology, you don't see a lot of numbers in biology, but you do run into them sometimes, like pH numbers, you might recall. Like an acid has a pH under 7, a base has a pH over 7. Those numbers are a simplification. The actual numbers are very, very tiny. And in fact, what you're actually seeing is the exponent in a scientific notation expression. So in other words, when you say a liquid has a pH of 3, that's actually the exponent. It's like 0.00000, something like that. So you do see scientific notation in a lot of places. And in fact, the Richter scale, which measures earthquakes, it's the same thing. That number they're reporting to you is actually an exponent because the actual number itself is so large that it requires scientific notation. Anyway, so let's get back to it. And yes, these will be made available to you on Moodle, so you can double check. And you always can ask questions. It doesn't have to wait till Thursday either. If you send me an email and say, listen, I don't get number 11. As soon as I have a chance, I'll get back to you and let you know why that is the case. All right, so here it is, scientific notation. So let's just go back and quickly review what we were doing before. And so remember, the point of this is to simply have a system for recognizing or representing, I should say, either extremely large or small numbers that would contain a large number of zeros. Okay, so for example, remember, and by the way, don't forget, all of these examples are based on exponents with base 10. Okay, it's understood that we're doing everything in terms of base 10. So when you see something like this, the first thing we're going to do is rewrite it as 1.22 times a million, or 1.22 times 10 to the 6th power. So the key is we always put all the digits after the decimal point, except for the first one. So no matter how many decimal digits there are, this comes before the decimal point and the rest come after. We don't need to write the other zeros separately because they're understood when we give us an exponent of 6. And, you know, I mean, you might not agree that this is easier or more convenient, but when the numbers get really large, like we start getting into the billions and trillions, this is much more convenient. Now, by the way, did I show this class I don't remember. I have found an example of when you might need scientific notation. It involved a dollar bill issued by another country. Does that ring a bell? Do you remember me mentioning this? I don't remember if I mentioned it to this class. No? Okay, all right, I'll tell you what. Just in case I didn't show this to you, I'm going to show you an example of when scientific notation might have come in handy. And what this is all about is there in about 2008, I'd say, there's a country in South Africa named Zimbabwe. And somehow or other, they managed to get themselves into a bit of a pickle with their inflation rate. That's right, inflation, remember? And so when that happens, they start printing money and they print money, and the problem gets worse and worse and worse. It got to the point, where they're issuing literally, oh no, I need a big picture of it. There it is, $100 trillion. Look at all those zeros. It's a lot of zeros to keep track of. So you know what? This probably was worth enough to buy a loaf of bread at that point in time in Zimbabwe's history. Their inflation rate was something like 80 quadrillion% every month. That's a big number. So these, they're resorting to printing out these $100 trillion notes because their currency is so worthless that $100 trillion is just about enough to buy a loaf of bread. So 100 trillion, let's make a note of that here. God, how many zeros is that? That's a lot. Now that's an awkward number. That's 1.0 times 10 to the 14th power. Now this is a case where I think you'll agree this is easier to deal with than this. Wow. Ooh, boggles the mind to think about this. Now, in the mean, of course, it's not like that anymore. They somewhere along the way they recalled this currency and they replaced it with something else, and they, of course, reformed their ways. The only way this can happen is if the central bank prints way too much money. But yeah, that's probably a record of some kind. And if you're a collector, you can get one of these brand new for $109, just because, wow, that's pretty cool. Anyway, so you do see these enormous numbers sometimes. And the other one you might run into is the storage on your computer. If you have a 1 terabyte hard drive, this means terabyte. Oops. The prefix tera means trillion. A byte is a single unit of storage on a computer. It's enough to hold one number, one character, or one letter. So a byte contains one piece of information. Your hard drive has enough room for 1 trillion bits of information or bytes of information. And that would be written as 1 with 12 zeros. That's a lot. We take it for granted. We're spoiled. 20 years ago, it would have been conceivable that any computer could have this much memory, much less be affordable by individuals. But here we're like, whatever. And this is equal to 1.0 times 10 to the 12th. Yeah, even within your lifetimes, you probably notice that computer storage keeps getting bigger and bigger very, very rapidly without the costs going through the roof. The technology just keeps accelerating all the time, which works in our favor, that's for sure. Anyway, so just as a review, it's helpful to remember some of these exponents. For example, 10 to the 6 is 1,000,000, which means, if you recall, 10 to the 9th is 1 billion. 10 to the 12th. All right, well, pretty soon we get tired of writing out all these digits. We can just write it out directly. Now, there's a 10 to the 15th, 1 quadrillion. And there are actual names for many of the ones that follow. In fact, maybe we could go to Wikipedia and see if there's a list there. Oh, here we go. Ooh, there are plenty. Look at this. We got billions. No, trillions. By the way, it turns out that these numbers, this discussion we're having, not every country uses the same notation or terminology that we do. I found this out in a very strange way. In Germany, in particular, they have slightly different names that we do not use. So their billion is our trillion, but trillion in English is 12 zeros. Quadrillion is followed by quintillion and sextillion and septillion, octillion, nonillion. Look at them all. Look how far it goes. Duovigintillion has 69 zeros. Now, here's one that you might find amusing. Google, the name of that search engine that you all know and love, is actually taken from the word Google, which means 1.0 times 10 to the 100th power. Or in other words, one with 100 zeros after it. Did you all know that? So whenever you use Google, just remember, it's, by the way, the reason why they changed the spelling is because they could not have copyrighted an actual word like that. Google. Okay. In other words, anyone could have stolen everything they do. So they just said, you know what? Let's just change it to Google. What the heck? That's what it sounds like anyway. And now we can copyright it and turn this into the name of our company. But Google is 1.0 times 10 to the 100th power. That's all it is. Interesting. Okay, let's have a poll. Who knew that? Oh, all right. It's all right. We don't have to have a formal poll. I'm going to say some of you may have. That's cool. Google, one times, yeah. See, now you're in the inside circle. You know the secret of Google. Oh, it was. Oh, wow. That's interesting. So they thought, well, you got to realize, I mean, these people who invented Google were probably mathematicians anyway, or at least they're very good at math. And so it stands to reason that they would have been well familiar with the word Google. And they thought, oh, that sounds cool. How can we make sure that we can copyright it legally? Oh, we'll just change the spelling slightly. Although it doesn't always, I mean, Apple didn't change the word Apple and they still were able to copyright it, now that I think about it. But I think they're afraid that people would mispronounce it and they wouldn't, it's just easier this way. So, okay. That was our fun fact for the day, I think. That's right. A lot of the names of things that we know and take for granted came from very unusual sources. It's not just Google. There's all kinds of things, like, for example, Starbucks. Oh, well, all right. I'll throw this one out there too. Starbucks is the name of a character in Moby Dick. Yes, it is. Okay, so there you go. Now you know the secret. He was one of the sailors on the Pequot with the mad Captain Ahab. In fact, there's a commercial on TV right now. I can't remember who it is. It's one of the insurance companies where a lady's driving around in the parking lot looking for a spot, and Captain Ahab is guiding her to a lot or a spot or something, as if he was looking for the great white whale. Yeah. So Starbucks comes from the novel Moby Dick, which you may have had to read in high school. Oh my God, what is this world coming to? Two of our favorite corporations have their names taken from very strange sources. Wow, where will it stop? Wow, interestingly enough, now you know that Apple has iTunes and all the rest of the music. For the longest time, they didn't have any Beatles songs. Why not? Because the Beatles had previously already chosen the name Apple for the name of their record label. And so there was all kinds of legal wrangling over that one. But enough, that'll be a story for another day. Okay. All right, here we go. Now, here's some scientific notation. Now, remember, the whole idea is to turn this into a number with a single, yes. So remember, they started Apple Corps in 68, I believe, and it was their own recording label, and they were hiring new artists and, to get them going and all, but the company was called Apple. In fact, if you look at the labels on any album issued from 68 on, it had the big apple on it rather than a green apple on the front. The back was the white part of it, the interior. And so Apple belonged to them, and somehow Apple was able to incorporate the name Apple, maybe because the British Apple was for the Beatles. Maybe there wasn't an American equivalent of it, but somehow both of them were called Apple. And this is what really held up Apple from offering the Beatles on iTunes for many, many years, because of all the legal fighting over the name Apple. So it's an interesting story, but yeah, see how these things happen, how these names can mean whatever, but we don't know why the Apple Corporation picked their name. Two guys named Stephen Jobs and Stephen Wozniak built computers in their garage in Southern California, and they thought, wouldn't it be cool to make a computer that people could have in their home offices? And man, what a crazy dream that is. This is going back to the late 70s, when computers were typically as big as a house and not very powerful. the idea that people could have one in their homes was just thought to be like a utopian fantasy, and yet they made it work. And that's why they're so crazy rich today. Yes, people who have visionary ideas like Jeff Bezos thinking, I wonder if people would buy merchandise online with this newfangled internet that's now available to everyone. So it's these visionaries who get there first with a great idea who often wind up being so crazy rich. All right, well, anyway, so here we go. So here's so 124. Now remember, you take the first digit and then the rest go after. So here we start with the 2 and the rest go after. Here we start with the 3, and then you just have to figure out what's the appropriate exponent. It's always times 10 to some power. And so here, this is 1.24 times 10 to the second, the third, and the fourth. You can kind of tell. Here's one way you can think about it. And this is something you may have been shown at some point before. If you have 1.24, how many places do I have to move this decimal to bring it back to 124? 2. Okay, now that's a very unscientific way of explaining this, but I think it works. Like, look at this one, 2.148. To get this back to the original 2148, I have to shift this decimal 1, 2, 3 places to the right, and that's the exponent, isn't it? How about this one? 3.2154. 1, 2, 3, 4 places to the right, and we're right back to where we started from. So therefore, the exponent is 4. Wow. Now, if you're not sure, I think your calculators are capable of doing scientific notation. Let's try this as an experiment. Let's say that you tried this one. Let's pick the last one. And you say to yourself, I'm wondering if I did this correctly. So if you go to your calculator, I'm pretty sure it can do this. If you were to type that and you multiply by 10 to the 4th, I think it has a special shortcut for this. You can do this directly with your x to the y key. 10xy to the 4th would give you this, but I think there's another key that will make this a little quicker. Let me just double check this. Here we go. I'm going to check this out on my calculator. Hold on one second. I knew it. All right. Here's what you can do. In order to save yourself the time of typing 10 to the 4th power, you can do this. 3.2154 times. Oh, wait, no, you don't even need the times. Hold on one second. Instead of the times, here's what you're going to do. If you notice, next to the 1, there's a button called EE. If you type it like this, 3.2154 EE4 equals, what do you get? 32,154. So what this does is it means that you did it correctly. Okay, now you're still the one who has to turn this into scientific notation, but at least this way you can confirm it very quickly and easily. You say, oh, that worked, therefore I must have done it correctly. And it works with negative numbers too. If you were to take, for example, 4.06 EE. Now remember, on this calculator, to make a negative number, you're going to hit plus and minus. That should do it. Let's check this out. 4.06 EE to negative equals, there you go. As we'll see in a few minutes, that would be 0406. So either plus or negative. Just remember that EE button means raise something to the 10th power. sorry, raise 10 to that power. All right, so, well, it looks like it's not going to be that difficult, doesn't it? And it's not really. You just have to get a little practice. Now, small numbers will require negative exponents, as you can probably guess. So let's take a look at these. Just a quick review. And so this is 1/millionth. And then this would be, let's say, 1/100,000th. A little awkward, but 1/100,000th. This would be 1,000th. I'll skip over to this one. This is 1/100th. And then 1/10th. Okay, now here's something that I find helpful. You may not agree with me, but if you look at this and you're looking at all the strings of zeros, you say, I don't get it. What is that supposed to be? Let's pick this one as an example. So when you have a small number like this, if you have a bunch of zeros and then something follows that, something other than zero, these are referred to as leading zeros. And so this is the pattern you might notice. The number of leading zeros is always one less than this exponent. Okay, so in other words, here I've got 3 leading zeros and the power is -4. Here I've got 4 leading zeros and the exponent is -5. With 5 leading zeros, it's -6. I don't know, that helps me remember. You don't have to, if this makes no sense to you, that's fine, but I personally think this is helpful because it's hard to, I mean, look at all these zeros. It's easy to get confused. Not only that, but to make things worse, at least on the positive side, like if you've got a huge number like 1 billion, you can put commas there and separate them out. You don't have something similar with the small numbers for some reason. By the way, this reminds me of another cool fun fact. If you've ever, I don't know, I'd have to look this up for myself, but it turns out, now you know that if you have a number like this means $1,000. Well, guess what? Not every country uses the same notation. There are countries that would write this in the following way. They reverse the periods and the commas. Now, you might say, well, what is this, some small islands in the Pacific Island? No, you'd be surprised. In South America, this is fairly common. I know for a fact that they do this in Brazil. And I think Germany too, because I know some German people, and I know from experience that they do this in Portugal. So, in fact, I was in a Starbucks in Portugal, and I looked at the cash register when I bought a coffee, and it said 3,00, and I was like, that's interesting. And then I remembered, oh, that's right, I'm in Portugal. Yes, it's insane. And so you know what that means, that if you have a calculator from one of those countries, it's been set up to reverse the commas and the periods. I know this from experience because I've had students from Brazil and they showed me their calculators and they're backwards from what we're used to seeing. That's right. You would think that somehow we would have all agreed, but it didn't turn out that way, did it? It's like the keyboard in a computer. Have you ever seen a computer that was built in a foreign country? Even in England, the keyboard isn't laid out exactly the same way. It's slightly different. And the first time I went to London, I was trying to send an email. I was looking for that little ampersand thing, at sign, to send an email, and I couldn't find it. It was buried way down in the bottom somewhere. How does this happen? Why do we all have different keyboards? Well, that's a little different because each country may have different symbols that they use that we don't use. And that's part of the explanation for it. But the rest of it, I'm like, well, why don't we do something about this? Why don't we standardize it? But there's not much you can do. Every country chooses its own standards, and that's that. So if somebody offers to sell you a calculator from another country, open it up and look at it and see if it's reversing the commas and the periods. Yeah, I was just as shocked as you were when I saw this for the first time, believe me. But when I saw this in the Starbucks in Portugal, I thought, oh, I know why it says that. Also, it has a euro symbol instead of a dollar, too. And of course, we know why that is, because they use the euro in Portugal. Interesting. And there's another fun fact while we're on the topic of fun facts. This symbol was actually chosen with a contest in Europe. The governments didn't just say, oh, this is the symbol, we're going to use it. They actually asked the people which one they liked the best. And this was the one that everyone said they liked the best. And so that's why that one was chosen. They actually asked people's opinion before they did something. How do you like that? All right, well, now let's carry on. So now how do you convert these tiny numbers into scientific notation? All right, this time we're starting. Now remember, we need a single digit before the decimal and the rest come after. So now we're moving the decimals in the opposite direction. Instead of to the left, we're moving them to the right. And look what happens. In order for me to convert this back to the original number, or actually to this number, I need to shift the decimal to the right 2 places. And here I need to go 1, 2, 3 to the right to make this number. And here I have to go to the right 1, 2, 3, 4 places to the right to create this number. So this is what I'm doing. Shifting the decimal a certain number of places to come up with this result. But these all have to be negative because these numbers are all less than 1. Okay, so therefore, as soon as you see it's less than 1, it has to have a negative exponent. All right, does that make sense to everyone? Beautiful. All right, so anyway, let's see how this works. Now, oh, by the way, once we're done with this part, we're not completely done with scientific notation. What we have to do is see how we can apply algebraic operations to this terminology or notation. We can actually multiply scientific numbers that are expressed in scientific notation, but we have to be careful with it. It's not that different than multiplying radicals in the sense that, remember with the radicals, we had something like this. Actually, no, like imagine a case like this. A radical B is multiplied by B, C radical D, and that turned out to be AC times radical BD. Something similar to that is happening here. We have to combine them in a very specific way. And what is that way? Well, here's an example of what I mean. What we're going to do is take these values and multiply them together. And then we're going to combine these two. Now, remember, these have the same base. So if I'm going to multiply 10 to the third times 10 squared, actually, it's common practice to use these x's for multiplication with scientific notation. We typically don't use that in math very often, but yeah, this is common practice to use that x to represent multiplication with scientific notation. So this could actually technically be written something like this, or something like this, but you don't usually see it done that way. Normally it's written like this. So what we're going to do is multiply the two coefficients, as they're called, and the exponents will be combined so that we end up in this case with 2.8. And remember, from the product rule, we add these together. Not what am I doing? Not 10 to the 15th, 10 to the 5th. So I multiplied the two constants, and then I've added the exponents because we have the same base, and that's my result. So, and you could double check this if you want to. The first number here, 2.0 times 10 to the third is 2,000. 1.4 times 10 squared is 140. If you multiply these together, come on, 2,000 times 140 is 280,000. And of course, that's what this is, 280,000. Remember, 10 to the fifth is 100,000. 2.8 times 10 to the fifth is also 280,000. Because 10 to the fifth is 100,000. So when you multiply 2.8 times 100,000, you get 280,000. So that means we must have done this correctly. All right, has everyone got that? Now, let's try some others. Oh, here it is. Yeah. That's pretty much what we just did. We're good. But as it points out here, this is based on the commutative property where, if you recall, this simply means that the order in which I apply parentheses to two products is not relevant because all we're doing is multiplying. All right, here's another nice one. I'm combining the 1.5 and the 3, and then the 10 to the fourth comes here. 10 to the negative 2 comes here. So the product of 1.5 and 3 is simply 4.5. And here I'm adding the exponents. 4 plus negative 2 is 2. And so I can either leave it like this, or if I need the actual number, I can write it out as 450. So it's pretty straightforward. I think you'll agree. Now, you know what I'd like to do, though? I'd like to show another example where you have to be careful. Sometimes you can run into issues here. Suppose we had something like this. 7.0 times 10 to the third and 4.0 10 to the sixth. Well, the problem here is that when you multiply these out, let's say you rewrite this as 7.0 times 4.0, and then you got here 10 to the third, 10 to the sixth. You've got 28 times 10 to the ninth. Now, the problem with that is that scientific notation requires us to have only a single decimal digit before the decimal point. So what I'm going to do is rewrite this as 2.8 times 10 to the 10th. This is not wrong. It's just not standard. it would normally be the case you would want to rewrite it as 2.8 times 10 to the 10th because it's the same thing. But here I only have a single decimal digit for the decimal point, which is what we're after. So in a case like this, you want to be careful with it. Well, what about division? If we can use this approach with multiplication, can we use division? Of course. That's right. We can divide as well. Not a problem. And so again, the logic is that we'll line them up to make sure that we're dividing out the coefficients and we're dividing out the exponents using the quotient rule this time. All right, so let's see some examples of this. Pretty amazing. So we divide the coefficients first, then subtracting using the quotient rule. Remember, the quotient rule is that a to the m over a to the n is a to the m minus n. So of course, if you're dividing 10 to the 5th over 10 to the 2nd, so there you go. Okay. All right, very good. Let's see an example. All right, so here they are. They're lined up nicely for us. So I can think of this as 8.2 over 2. And over here, I've got 10 to the 7 minus 5. So this is clearly 4.1. And this is now 10 squared. And I could write this or leave it like this, or I can just turn it into 410. It depends. It depends on what you're being asked to do. But if I need to, let's say this gives me a price, let's say, I don't want to know that it's 4.1 times 10 squared dollars. Then I need to know that it's $400. But if I'm just trying to write it out in scientific notation, I would just leave it as 4.1 times 10 to the second. All right, how about this one? Give it a second to catch up. Very good. All right. Here we go. Here's a good example. So you can see I've got the coefficients are 3.9 over 3. Over here, I can consolidate the two exponents using the quotient rule, 5 minus 8. So this turns into 1.3. And here I have negative 3. And again, if you want to write this in scientific notation, now remember, here we're going to have some leading zeros. I mentioned the rule before. That means there's going to be 2 leading zeros. And so there you go. And if you forget, watch what you can do. You can say, well, you know what? Is this right? I know. Let's check it out. How many places do I have to shift that decimal to the right to give me this 1.3? 1, oops, 2, 3. Oh, yeah, look at that. 3 places to the right, and I've got my 1.3. Now, then the other option is, like I said before, go to your calculator and type 1.3. If you really need to convert this into the a decimal, just put 1.3 EE 3 negative equals. All right, don't forget what EE means. That's 10 raised to some power. So do it on your calculator, 1.3 times. You don't need the times. I just realized 1.3 EE takes care of that. 3 negative equals, and you're good. All right, so that was our brief review of scientific notation. Now, what's coming up next is a little bit more challenging. Now, remember the other day we looked at a video where they talked about the Fibonacci sequence. And so a sequence is just basically a string of numbers that has a specific pattern to it. But we're going to look at a couple of simpler versions of Fibonacci. Fibonacci is a fairly complicated sequence. We're going to instead consider two other types of sequences. And those sequences are known as arithmetic and geometric sequences. And these have a lot of interesting applications and properties. And really, it's just a list of terms. It's not even a set, it's a list of terms that has a pattern to them that we have to figure out typically. And so each item or each element in this list is called a term. Although you can call them elements if you want to. Each one is a term in the sequence. Now this one, it's pretty obvious that what comes next is 7, 8, 9, 10, because you can see the pattern. We started with 1, and every time we increase, the next term is always the previous term plus 1. Okay, so this is 1 plus 1, 2 plus 1, 3 plus 1, all the way out. And it goes on, of course, to infinity. That's why the 3 dots are there. So anyway, so the idea of the sequence we've already run into, it's just that these are different kinds of sequences. The patterns are different. And it's the pattern that determines what kind of sequence it is. But once we know the pattern, we can figure out any term we want in that sequence. So, yeah, so like I said, there's 2 basic types, arithmetic and geometric. And we'll start with arithmetic because it's simpler. And it turns out there are formulas that we can use, but we still have to understand them. Now, in this particular case, the calculator isn't really going to be all that helpful because what we're doing is not actually built into it, but we can still use it to come up with the results if we know the formulas. All right, so let's see what those formulas might look like. Here we go. Now, first of all, what does it mean to be an arithmetic sequence? This is a sequence in which the differences between the consecutive terms are constant. So the one we were just looking at falls into this category because each term is 1 greater than the one before it. So here we have a common difference of 1. In other words, in order to go from one term to the next, all I did was add 1 in each case, and that never changes. So we have constant differences, and therefore, this is an arithmetic sequence. All right, so they don't look so terrifying, do they? No, that's because they're not. Not like the Fibonacci sequence, which is actually quite a very advanced idea. This is different. It's just 1, 2, 3, 4, 5, 6, all the way up. It is basically a sequence of the natural numbers. All right, so we have some other examples here. When you'll see in each case, what your job is to figure out, first make sure that it is an arithmetic sequence and figure out what the common difference is. So this one we already know. What about this one? Is this an arithmetic sequence? It sure is, because the common difference is 3. And by the way, it doesn't matter where it starts. It doesn't have to start at 1. As long as there's a common difference, here it's always 3. To get from 2 to 5, I added 3. To get from 5 to 8, I added 3, all the way up. And this goes on forever. That qualifies then as an arithmetic sequence. Now look at this one. Oh my God. What happened? They're going down. And why is that happening? because the common difference is negative. We're adding, in effect, adding -1 to each of these terms to get to the next term. And so because the common difference is negative, they keep getting smaller. So this one is actually going down to -infinity. This one is going up to positive infinity, but this last one is actually going down to -infinity. That's right. And of course, we love infinity. We already know that there's different kinds of infinities. And we know that if you're clever enough, you can fill up an infinite hotel, but just by redistributing all the guests with a very specific pattern. All right. Now, what if I asked you this question? Suppose I'm looking at this last sequence. I say, oh, by the way, this is the first term. Let me just mention this. This is called the first term. And we're going to use the following notation to represent that. We're going to use the letter A for that. This will be A1, A2, because that's the second term. This will be, of course, A3, A4, A5, all the way up. If I wanted to know the identity of, let's say, the 100th term, I could write them all out, but that could take a while. It turns out there's a formula that will let me do that directly. And that's what we're going to do next. But it's a fairly complicated process. So you know what that means? We don't want to rush through it, do we? No. So that means we can save it until Thursday. But remember, on Thursday, we're doing the second chapter, chapter 5, problem set number 2 first, and then we'll dive back into this fun stuff. All right, so don't forget about number 2. Oh, you've seen that. Interesting. It's not that complicated, but I don't want to rush through it either. Yeah, let's do this. So for Thursday, we'll go through the second problem set from chapter 5. It's longer than this one, so it's going to take a while. But when we're finished with it, we'll get back to our scientific our sequences, and we'll see how this works. Anyway, so in the meantime, unless there's any last minute questions, I guess we have to knock it off for the day. I know it's always disappointing when this class is over, but good things always come to an end, don't they? All right, so I guess I'll just see you all next time.
Thank you.
Okay, you're welcome.
Thank you.
Thank
Okay,
you.
bye.
Bye.
See you later.